Thank you, Diego. And I have to say, it's a pleasure to be here. Thank you for organizing this. It feels like being back with my mathematical family. Mm-hmm. So it's, as I said, it's a pleasure to be here. So today I'm going to talk about, regularity for the general elliptic operators, and this is work in progress. We're going to start with just a review of the classical theory, because I don't know who the audience is, how much do you know about, the Georgian Moser stuff, and then a little bit about the recent progress in collaboration, and then the one small new result. So the collaboration is with Korobenko, Sawyer, and Shen, and there is a recent, relatively recent publication in the memoir where we had a big chunk of this theory that we're trying to develop for infinite degenerate elliptic equations. So let's review a little bit. And if you ever taken, I guess that's a PDE course, you probably heard about the Sobolev embeddings. And the idea is the Sobolev spaces are ways to measure regularity for functions in a more weak way. So we have the notion of weak derivatives in LP. And the embedding, for example, when Sobolev space for P is between 1 and n, are spaces where the function is in LP and the gradient is in LP. And in that case, the LP gets a bump. So the function is not just in LP, but it's in LP times n over n minus p. So it's a little better. And when p is bigger than n, well, you even get Helder continuity. But the one we're gonna mostly concentrate on is in the first one. So this is the first ingredient of the theory, is that, well, there is a bump just by the space where the solutions live. The function is a little better than the LP where it started. Then the whole probably reason to create these Sobolev spaces was to be able to define weakly solutions to elliptic operators, for example, among other ones, right? So the idea is when we look at an elliptic operator in the versions form, and where A is an elliptic matrix, is basically all the eigenvalues are equivalent to a constant, and that's more or less is a generalization of the identity. And then the weak formulation could be thought as in terms of bilinear forms, right? In Hilbert spaces, if you want. So we say that U is a weak solution, U is in W12, if when we test it against any function that vanishes on the boundary in the same space, then equals, well, the functional tested with whatever the right-hand side is. I mean, if the right-hand side is 0, this will be 0. I just put here a first order term. There could be also derivative terms here, but for the sake of the talk, I just left it like that. So the Georgi-Nash-Moser theory then, one of the first things that you get when you have a solution is you notice that immediately from the solution, you have of course, your gradient is in L2 by hypothesis, but not only that, it's actually bounded by the L2 norm of the function. So the equation in some way already gives you a gain the other way from the function to the gradient. And the idea of the iteration is simply, well, we have the implicit gain from the Sobolev embedding from the gradient to the LP norms. So if we put those two together, then we have a machine. That's the idea. So this is what happens in the Moser iteration. So between the first, between the embeddings and the Cacciopoli, which give us comes from the equation, and a smart choice of test functions, we get the iteration inequality, which is a machine you can crank to get better and better estimates on the solution U. So here you see we have a U is in L2 beta, but then you pay us a price with a constant, and then you get that U is in L2 beta times a factor. And that's, the idea is, can you, do this infinitely many times, and then you will get that the function U is bounded. So this is sometimes called the weak Harnack for solutions. And yes, I mean, by smart choices of cutoff functions and balls and things like that, you get this kind of estimate for all P bigger than 1 with some dilation constants there. And the right-hand side, norm is Q over 2, norm Q over 2, where Q is bigger than N. So this is important in the computations, because this extra gap between the gap that we get from the Sobolev and the norm for the right-hand side is actually exploited in the computations to make these inequalities work. So the next step is, so they give us boundedness for sub-solutions, or just think solutions in general. And then by considering basically 1 over U, you get estimates for the infimum of U. So for non-negative solutions, you can have an upper estimate from a lower estimate for the infimum, and then there is a magic glue in between them. So you have here, this is the LP norm of 1 over U, and this John Niedemek estimates sort of relate those two. So basically, we can estimate the LP not norm of U by a constant times the LP norm not of 1 over U. And by putting all these elements together, the 2 weak Harnacks and all this glue, we obtain an estimate of the oscillation, and that gives us what we wanted, which was prove Helder continuity. So this is basically the Georgi-Nash-Moser theory in a nutshell. This is a very robust machinery. It has been exploited in many environments, including there's a recent 10 years old, book on nonlinear potential theoremetric spaces by Bjorn and Bjorn. And this same machinery has been generalized to Newtonian spaces, which are basically, and it's a super generalization of these Sobolev spaces to where you don't necessarily have derivatives or gradients, but you have what we call upper gradients, which function like the gradient when you have some kind of fundamental calculus estimate there. It's important to know that, I mean, all these things actually have to do with doubling measures, and all the results that are obtained in general, well, I mean, they require some kind of Poincare estimates if you don't have them for free, and then all the machinery works well. I mean, you end up having Helder continuous solutions. So some of the things that make this work so well in so many different environments are that the LP norms are actually really, really nice. So we know what the LP norms are. They can also be written as in the like a Luxembourg norm way. And they are continuous in P, including all the way up to infinity. We take the LP norm of the LP norm, we get the product of the norms. I mean, and there are very nice Helder's inequalities and interpolation inequalities that we can have. So all this makes all these I have to say generalizations in some way pave the way for that. Now, a few years ago, with Luda Korovenko and Diego Maldonado, we published a result about the weak Sobolev embeddings. Implies actually that the underlying measures must be doubling. So this is what this fact is saying is that precisely that if you have any gain in the as a power of P from in any Weak's type of Sobolev embedding, then necessarily the measure cannot be non-doubling. And why do I care? Well, because I'm trying to work on with infinite degenerate elliptic equations. And those equations have an inherent geometry associated to the matrices, you know, this Pfeffer-Marfond geometry. And that geometry will be non-doubling if the operator is infinite degenerate. So then the question of what do we do in non-doubling spaces is the same as asking what do we do with infinite degenerate elliptic operators in some way. Okay, so some of the recent progress that I mentioned with Eric Sawyer, Korovenko, and Shen, I'll just talk about some easily understood results. So we looked at a baby model where basically in R2, we have a vector space, a vector field that is non-degenerate in one dimension, but in the other, it gets smaller and smaller as it approaches x equals 0. Okay, so it gets very, very small, and it gets small with infinite order. So for this baby space, we computed geodesics, and we look at what the balls look like. So this is some of the geodesics and a quarter of a ball, what it looks like. So they're highly non-doubling things. So this kind of are the pictures that we have. So in this, for these particular spaces, we got some positive results in which we basically extended the Georgi-Moser-Nash theory. So for example, if instead of just doing it in 2 dimensions, we put an n-1 identity, and we just let this vector field degenerate to infinite order in only one of the dimensions. In that case, we actually get boundedness of solutions. So basically get this weak Harnack inequality for subsolutions as far as the function goes to 0 in order such that the minus the logarithm of that function f is 1 over a power r to the sigma, where sigma is into 0 and 1. And this is more or less sharp, because on a higher in dimensions at least higher than 3, we actually have counterexamples. If sigma is bigger or equal than 1, we show examples where we have weak solutions that are actually unbounded. So this is a pretty nice result. Even though it's a very, very small, how to say, boutique problem, it's one of the first things that we're trying to understand what happens when things that degenerate to infinite order. Continuity is a little harder. So we got some results in dimension 2. And again, for some particular, very particular orders of vanishing. K, by the way, K is how many logarithms you're taking, okay? And sigma is the powers of those logarithms. So I'm not gonna dwell in the exact meaning of all this, but all I wanna say is that we have some very nice results, and we show that actually we can get continuity in some particular cases in 2 dimensions. All this theory relies on an abstract theory that instead of using, of course, LP norms, we need to consider Orlik norms. So Orlik norms are based on this idea of Young functions, which are generalizations of basically the powers P. And instead of the LP norm, we use the Luxembourg norm. There is also a concept of a conjugate function, an idea of a Hölder's inequality, right? The biggest problem, the biggest technical problem in dealing with these norms is that they are not as nice as the LP norms. I mean, if you try to compose 2 of these together, well, I mean, they don't behave so nice. It's not as clear. They don't compose so easily. So we have to come up with particular examples. So I think it was Eric came out with this beautiful idea of looking at Young functions of this shape, of this form. So we just take a function g, compose it with g inverse plus a bump. some little mu bigger than 0, right? And of course, if mu is 0, you just get t, right? But if g is, for example, in our case, the exponential of t to the m, then what you get is some kind of, well, a Young function, which is a little bigger than t to the 1. So phi of t over t still goes to infinity and infinity, but phi of t over t to the 1 plus epsilon goes to 0 for every epsilon, right? And other than that, they're very nice functions. I mean, their derivatives behave almost like powers. They are submultiplicative, and also you can recover the L infinity norms. I mean, if you define clearly how it goes. By the way, we only define this basically behavior at infinity. Near 0, we just make them piecewise linear and nice. Okay, so with these functions, this is the new result that I wanted to talk about. Is basically a weak Harnack for subsolutions. It's a generalization of what we did before. I mean, the biggest difference, I guess, it comes in this part over here, which is instead of just before this function phi, it had to be what we call it admissible, and it had to be basically in the dual space of W1, 2 with the weights. So with the A weight in there. So now it just needs to be in the adjoint space for the Young function, where this function psi is actually like the square root in composition. So psi composed with psi is phi. And it turns out that this is not a big deal, because what happens here is, by the way these functions are defined, if you just compose phi mu over 2 with phi mu over 2, you get phi mu. So it's kind of a nice magic trick there that happens at least for t big. So for these functions here, we assume that we have a Sobolev embedding, with the Young function, and the Sobolev, we call it the phi little phi Orlik Sobolev bump inequality, because because of the bump type of function that we have, and this little function phi is just a growth, because this R, it's allowed to be not just first power. It could depend in some weird way, but it would still go to 0, although it could go to 0 very, very slowly or very fast, depending on the circumstance. So this is the new result, and we still get the boundedness of solutions. A little bit about the proof, maybe, is again, is similar to what I showed at the beginning of the classical result, where we get an iteration inequality. So this iteration inequality, it has to do with that square root function psi, and it's a little more complicated than the previous one I showed with the Sobolev embeddings. But still, these mu j's are just a sequence of balls, concentric balls, that goes to a half a ball or something like that. And it turns out that for these particular Young functions, we can actually prove that, if we take the lim sup of the inverses of these quantities here, so if we define them iteratively by this expression, then we can express this lim sup bounded by the initial term to some power, some power like looks like this. So that's I think that's about all the time I have. Yes. So that's it. I think I'm out on time.